Hello everyone, this video is about machine learning based survival analysis using the Scikit Survival library of Python. Scikit Survival is a Python library or package that is built on top of the scikit-learn library. This scikit-learn library is actually a standard machine learning library in Python, which is simple and efficient for conducting different types of data analysis related to classification, regression, clustering, and dimensionality reduction. Besides to the different types of data analysis, scikit-learn has also important functions related to model selection and that of data preprocessing. So the Scikit Survival library, which is a Python library for conducting survival analysis, utilizes the major functionalities of scikit-learn, especially for pre-processing data and for selecting a model from different candidate models. So in this video particularly we'll see the preparation of survival data, and we'll consider the machine learning version of the standard Cox proportional hazards model, and we'll also consider the performance measures because the survival data is different from that of data that we use for classification and regression problems. So the performance measures used for regression and classification problems are not applicable. So there are different measures for checking or measuring the performance of the different survival models. We'll also consider the penalized versions of the Cox proportional hazards model, and then we'll look at the random survival forest, gradient boosting survival model, the survival support vector machine, survival tree, and extra trees survival model. And lastly, we'll see how to determine the relative importance or contribution of the different variables that are included in the particular survival model. So here the scikit survival, like that of the scikit-learn, which has its own documentation, as you see here. Scikit survival has also its own documentation, which is very detailed and brief. So here you can look at this documentation of the Scikit survival library of Python. And here, for example, the penalized Cox models are also described here, and that's of the random survival forest is also available, or the description can be found in the Scikit survival library. Gradient boosted models are also available in this documentation, and the survival support vector machine is also there in the Scikit survival documentation. In addition, for evaluating the survival models, it's available here, including concordance index, the cumulative dynamic area under the receiver operating characteristics curve, a Blair score, and basically we could classify the different measures of the different performance measures of survival analysis into three, something like measures utilizing the time-dependent risk scores, and that's of the measures utilizing the hazard functions, and there are also measures utilizing that's of the survival probabilities. So the documentation is very detailed, and it is actually very clear, so you can go to this documentation for more information. So today we are going to consider some common survival models. First, we'll consider the Cox proportional survival analysis, which is actually similar to the standard Cox proportional hazards model. And we'll see the Coxnet survival analysis. This is actually the penalized version of the standard Cox PH model. So this Coxnet survival analysis combines the L1 and L2 regularizations, or it makes a balance between that of a rich Cox PH model and a lasso Cox PH model. We'll also consider random survival forest, extra survival trees, gradient boosting survival analysis, and component-wise gradient boosting survival analysis, which are these actually what we call ensemble methods. And we'll see also the survival support vector machines, fast survival support vector machine, and that's of naive survival support vector machine. Actually, this naive survival support vector machine is something like a regression model directly applied to the survival times without considering the censoring events. In other words, this naive survival support vector machine assumes that the event happened at the censored time. So in this modeling, it's just a regression model directly applied to the survival times. And we'll also consider a survival tree, which is similar to the standard decision tree that can be utilized for regression and classification problem. So first we have to install the latest version of scikit-learn and scikit-survival. So here just by running this code you can install these packages, but sometimes this scikit-survival may not be installed successfully in Jupyter Notebook or Jupyter Lab. So in that case there may be a need of creating a virtual library, or you can take the notebook to Google Collaboratory or Colab, and you can just utilize the built-in libraries in Colab. Otherwise, in this Jupyter notebook or Jupyter Lab, this scikit survival library may need to create certain virtual library so that all the required packages are going to be installed, in which those libraries are compatible to each other. So first let's load the data that we are going to use for illustrating these survival machine learning models, and for that we usually need these two common libraries, NumPy and Pandas. Then I put the data into my GitHub repo so I can read the data using this pd.readcsv. So this is the data that we are going to use today for demonstrating the application of machine learning models for survival analysis. So here we have variables like card number, age, gender, employment type, clinical stage, functional status, number of CD4 counts, defaulter in survival time. Actually, this data is data related to HIV patients. So here the objective is to determine factors affecting the patient's defaulting status from that of the highly active antiretroviral therapy treatment. So here this defaulter indicates whether an individual is defaulted, which may be due to death or being transferred to other hospital, or in general it could be lost to follow. So for today's illustration, this is our event of interest, whether a patient was still active on the treatment or whether the patient was defaulted due to different reasons, including death, loss to follow, and that of being transferred to other hospital. So this survival time is nothing but that of the time to default. So individual 1 is active, and let's say he stayed in the treatment up to around 27 months. The second one, the same, is active and stayed for about 33 months, and so on. And when it comes to that of patient number 4, the patient actually defaulted at that of 3 months. So here there are 1464 observations and 9 columns. That means we have 1464 observations and 9 variables. So here we have card number. This has nothing to do with our analysis, so card number is not going to be considered as a covariate or as an outcome. And here defaulter in survival time are going to be considered as our survival dependent variable, or these two variables will be considered as a dependent variable for our survival models. And all the other variables like age, gender, employment type, clinical stage, functional status, and CD4 will be considered as covariates. We can look at some of the descriptions related to these variables included in our dataset using the .info method. So here we can see that cardinum it has 1464 observations, so there are no missing observations. Age is the same, gender, but when we come to this employment type, there are 1444 observations which are non-missing. Then that means there are some missing observations for this variable, and all the other variables have no missing observation. And the other here, gender is object, employment condition object, clinical stage object, and functional status is also object. So for this particular dataset, the values of gender are entered as female and female, or the values are strings. Similarly, for employment, clinical stage, functional status, the values are entered in the form of string. Therefore, the data type in Python becomes object for that of gender, employment type, clinical stage, and functional status. And for the other variables, age and defaulter, their values or their data type is actually int, and that's of here just we have float, and here we have again integer. But for that of card number, it says int. Actually, even if the type is int, we know that this card number is just an identification, or it's not a quantitative variable in general, or it is a qualitative variable, which is actually something like numerical codes. And we can check also whether there are missing observations or not using this is in a method and then calling that of sum. And here actually if I add a new cell here, now RTDF is our data that is imported from my GitHub repo. Then over this data frame object, if we call this is an a method, then it provides this data frame where it checks whether each observation is missing or not for each variable. So here it's not possible to actually examine whether the variables have some missing observation or not, because it checks each variable or it checks each observation of each variable, and it returns false for those non-missing observations, and it will return true for those missing observations. Instead, if we call the method dot sum over this is in a method, in that case it will add all the values of each variable. Cardinum, these values will be added, age, gender, and so on. Therefore, these values are actually Boolean. That means false represents 0 and true represents as of 1. So if the sum of these values is different from 0, that means this variable has a missing observation. So if I run this, it becomes like this. So there are no missing observations for most of the variables, but there are 20 missing observations for the variable implement type. So the first thing that you have to do is just to examine our data set that will be used for our particular data analysis. Then in case when there are missing values like this, we have to consider imputing the values using the different types of missing value imputation techniques. But for today's illustration, I'm going to use these missing values as they are, and we will see how the machine learning models treat these missing values. But keep in mind that these missing values should be actually imputed using the different imputation techniques. Then next we need to separate the covariates and outcomes data into two different data frames. So for the covariate data frame, we have the variable cardinum. This cardinum has nothing to do with our covariates or outcomes data, so this should be dropped. So for this covariates data frame, we need to exclude the variables card number and this defaulter and survival time, which are our outcome variables. So if I run this, now there are 1464 observations in our covariates data frame, and there are 6 columns. That means we have 6 covariates: 1 age, 2 gender, 3 employment type, 4 clinical stage, 5 functional status, and 6 seed for count. So we have 6 covariates to be included in our particular machine learning models. And regarding the outcomes data, we need to have that of the our event of interest, which is actually defaulter, and that's of the time to event variable, here what we call the survival time. So for the outcomes data frame, wide if we can extract these two variables from our original data frame. So if I run this, now here again there are 1464 observations, and we have 2 columns, or we have 2 variables that are going to be considered as an outcome variable for our specific survival data analysis. Then once we separate the coverage and outcomes data into different data frames, like XDF for the coverage data frame and YDF for that of the outcomes data frame. Next, there is a need to split the data into training and test sets. It's also possible to include a validation set, but for now, let's concentrate on splitting the data into train and test sets. So for this purpose, we need to import the function train test split from sklearn model selection. Then we can apply this function just giving the coverage data frame, the outcomes data frame, and here instead of making a completely random split, it's better to consider what we call a stratified random split, because you have here an event of interest defaulter, and sometimes the number of events or the proportion of events may be very small. Then in that case, in order to have a certain proportional number of events between the train and the test data frames, it is better to use stratified train test split. So here, stratify, we have our outcome data frame YDF, and the stratification is going to be based on this our event of interest defaulter. So it's better always to consider a stratified random split instead of a completely randomized split, so that there could be a proportional number of events between the train and test data frames. Let the test size be 0.30. That means 30% will go for testing, and 70% will go for that of training. This random states is nothing but can be any number, just it is for reproducibility purpose. So now the train test split is done. We can view the train data frame like this. In the train data frame, there are 1024 observations, and we have 6 columns. And here you can easily observe that here these indices are randomized, because in the train test split, randomization is applied specifically here, stratified random split. So here it's expected that these indices will be randomized, or they will not be in order, or they will not be arranged in an increasing or decreasing order. But in general, here we have 1024 observations and we have 6 columns. Similarly, we can also look at that's of X test def, that's of the test data frame of the coverage data. So in the test, we have 440 observations and 6 columns. 6 columns. We can also view the shape of this train input features data frame and test input features data frame. So there are 1024 observations in the training data frame and 440 observations in the test data frame. Similarly, we can also look at that of our outcomes data frame y trained f. This one I can view this as this. There are 1024 observations in the train outcomes data frame. There are 1024 observations in the train coverage data frame. Similarly, we make y test df. There are 440 observations in the outcomes test data frame, And again here there are 440 observations in the covariance test data frame. And we can also just look at the shape y train f dot shape, which shows the number of observations and number of variables dot shape. So there are 1024 observations in the train outcomes data frame and 440 observations in the test outcomes data frame. So we can also look at the information. Actually, we already saw the data information related to our original data frame. Here we can also look at the information related to the different variables that are included in our covariance data frame. So here we have age, it is an integer, gender, employment type, clinical stage, and functional status are objects. So specifically for this particular dataset, all those variables with data type of object are qualitative variables, and all those variables with a type of int or float are quantitative variables. So here age and CD4 are quantitative, and all the other variables are qualitative. So next we need to identify the categorical and that's of quantitative covariance. So as I said before, here in this particular data frame, those variables which are not object type are quantitative variables, and those variables which are object type are qualitative variables. So here these quantitative features are nothing but those variables whose type is not object. So list those variables whose data types are different from objects, or says exclude object. So this will extract those objects or those variables whose data type is not object. So here age and CD4 are our quantitative variable of interest. And for those categorical features, they are just all the variables with data type of object. So here we have two quantitative covariates, and we have four qualitative categorical or qualitative covariates. Then once we identify these categorical and quantitative covariates, next we need to transform our data set. That means the qualitative variables should be numerically one-hot encoded, and the quantitative variables also need a transformation of standardization or normalization. So next we need to instantiate our data transformer, and for this purpose we can import one-hot encoder, a standard scaler for standardization, and min-max scaler for normalization from scaler pre-processing. So I can run this cell. Now this one-hot encoder, standard scaler, and min-max scaler are imported from scaler pre-processing. So one-hot encoder is going to be used for one-hot encoding or creating dummy variables for those qualitative covariates. So first we need to instantiate this one-hot encoder. Let's say one-hot encoder, let's say drop first. Now here the first category of each of the qualitative variable will be considered as a reference category. So one-hot encoder, then drop first. Let me run this cell. Now this is just an instantiation of our data transformer, specifically the qualitative data transformer, which is called one-hot encoder. So if I point to here, it says not fitted. That means we didn't one-hot encode any qualitative variable. And if you are interested, you can look at the parameters. Here we have, for example, drop first, because here we set the first category to be considered as a reference category. Yeah, so there are also other parameters, but if you are interested, you can click here and go to the documentation for one-hot encoder. So here, this is the one-hot encoder documentation. So here it shows the different parameters for making one-hot encoding, and the description of each parameter is also available here. Now, this is just an instantiation. We didn't convert any categorical or qualitative covariate yet. So for converting, next what we need to do is we need to call this instantiated transformer and call fit underscore transform. Then, for example, for our data frame, let me say here just before that, let me create a new cell and let me say just our data frame is XDF. So XDF, from this, let me extract just these variables. Let me copy this and let me assign this to a variable qualitative ops. So this just okay. Oh, so here I need to put that of the list of the covariates inside the brackets. Data frame object is not callable. Okay. Data frame object is not callable. So here, instead of this, we have to use that of the square bracket. So this one. So now these are those qualitative variables. So we just here instantiated our qualitative variable or categorical variable transformer. So categorical transform dot fit transform, and here I have to specify these qualitative variables. And let me run and see the outcome. Now it says, yeah, now here the pre-processing is done, or each variable is one-hot encoded, but says compressed sparse row sparse matrix of data type 464 with 3698 stored elements and shape. It is 1464 and 10. This is just for reducing the memory size. The data is presented in terms of sparse data matrix, and actually here to view the data, here we have the option sparse output. By default it is true, so here, for example, we can set it to false so that we are able to see the data. The transformation is actually done, but since it contains so many ones and zeros for just reducing the memory size, it presents the data in terms of what we call sparse matrix. So to view the data, we can just here add this sparse output false, which is actually true by default. So let me run it again, and we can see here drop first, we have set it out here. Sparse output, we set it to false. Here we have these qualitative variables to be transformed. Now let's run this again and see what the result will look like. So here the transformation is done. Therefore, that means each variable gender is one hot encoded, taking the first category as a reference, and employment condition, and clinical stage, and functional status. And the same applies for that of standard scalar. This is for standardizing each quantitative variable. We can use standardization or normalization, but usually it is assumed that if we assume those quantitative covariates are normally distributed, standardization can be used. But if we do not assume any distribution, we can use this min-max scalar or normalization, which determines or which normalizes each quantitative variable into a value between 0 and 1. Actually, there is no hard and fast rule which transformation to be used, but we can consider it as a hyperparameter, and we can try to fit using this standard scalar and also using this min-max scalar, and it is better to select the one that works best. But for us, for now, let's use this standard scalar or standardization. So for standardization, again, we need to instantiate this model, and let's assign it to the object quant transformer. Let me run it. Now we can see here, because it is standardization, it uses the mean and standard deviation of the quantitative variables. And yet the transformation is not done. It says not fitted. And if you are interested, you can click here and look at the documentation of standard scalar. Here is the documentation of the standard scalar with all the parameters, and here there is a description. So like that of the categorical transformation, here we need to call this instantiated object and call the method fit underscore transform, and here we need to provide our data to be transformed. Our data, let's say x df, and our variables are I think the first one is age, second one is cd4, and let's see the outcome of just executing this cell. Yeah, now these two variables are normalized with a mean of 0 and a variance of 1. But instead of transforming the qualitative and the quantitative variables separately, we can mix transformation both in one. And for that purpose, we need to call the function column transformer from a scalar compose. Then utilizing this function, we can make the transformation of both the categorical covariates and the quantitative covariates together. So once we import this function, once this function is imported, we can call this function column transformer and then supply these transformations in this form. Cat transform, this can be anything. Let's say categorical transformer, categorical encoder, then for which variable, for which transformer, for the cat transformer. This cat transformer is nothing but the one that is instantiated here, this cat transformer. For which variables? For the categorical features. These categorical features are those features that are listed here. gender, employment type, clinical stage, and functional status. Similarly, for the quantity variables, here we can call anything, but let's say scalar. Therefore, this quantitative transformer, this quantitative transformer is actually the transformer here. For which variables? For those quantitative features. Quantitative features here, these two quantitative features. So we can run this. Now we instantiated the transformer for transforming both the categorical and quantitative covariates, but the transformation is not done yet. And you can also go to the documentation for this column transformer so that you can be able to see how this column transformer transforms those qualitative and quantitative covariates. So here in this column transformer, here we have parameters, transformer, cat encoder, and scalar. These names. So this name is for the categorical transformer to be applied on the categorical features. And this scalar is for the quantitative transformer to be applied on the quantitative features. So next, for the categorical encoder, it's going to be applied on these qualitative variables, and for the quantitative we have this age and CD4. And for the one-hot encoder, we have the first category to be considered as a reference category, and this is per the output. It doesn't have any significant impact actually. So, and for the scalar, we have this mean and standard deviation of each of these variables. So here we instantiated our transformer for transforming both the categorical and quantitative covariates together. So here we can first transform the train data frame. Once we instantiate our transformer, first we have to transform the train data set. So we need to call this method transformer, and over that we need to call the method fit underscore transform and supply the training data. So let me run it. Now this is the transformation of the training input features. Now this transformation considers both the qualitative variables and the quantitative variables, where the qualitative variables are one-hot encoded or dummy encoded, and the quantitative variables are standardized with a mean of 0 and a variance of 1. Next, once we transform our training data, we need to transform the test data. Then for transforming the test data, we need to call the method transform instead of fit underscore transform. So first we need to transform the training data frame using this fit underscore transform, and then we need to apply the transform method for the test data frame. So for the training we use fit transform, and for the testing we use transform. So let me run this. Yeah, now the transformation for the test data frame is also done. So here when we use fit transform, now for those quantitative variables, the mean and the standard deviation of each variable will be stored in this transformer. Once this mean and standard deviation of the training dataset are stored here in the transformer, this mean and standard deviation are used for transforming that of this test data frame. Therefore, that's why we use fit underscore transform for the training data, and transform for the testing data. We can look at the shape of these data frames. Let's say run. There are 1024 observations in the transformed train dataset, and there are 440 observations in the test data frame. So 1024 and 440 in the train and test sets respectively. So if we go back to the original train and test data frames, yeah, there are 1024 observations in the train data frame, 440 in the test data frame. Then and here there are 12 input features in the transformed train data frame and 12 input features in the test data frame. But here in the original train data frame there are 6 variables, and the test again there are 6 variables, but in the transformed it becomes 12, right? Therefore the reason for this is here we have some qualitative variables with more than 2 categories. Then in such case these qualitative variables with more than 2 categories are represented by 2 or more dummy variables. Due to that, the number of input features or the number of covariates in the transformed data frame increases to 12. So specifically, we can look at each data frame, let's say X, DF. First, let's consider sex. Sex has, or the of gender has only 2 categories, so it doesn't have any impact. Let's say values. Value, I think, counts. Okay, value, this counts. Oh, here we don't have a variable sex. Here what we have is gender. So here we have female and male, 2 categories. The second one is employment type, emp. Now here we have unemployed, full-time, not working, and we have part-time. Therefore we have more than 2 categories. And the same is true for clinical stage, and the same is true for functional status. So due to these qualitative variables having more than 2 categories, their one-hot encoded variables are more than 1. So due to that, we have 12 covariates in the transformed input features data or in the transformed covariates data. And we can also get the names of the transformed covariates data frame or the transformed input features. So cat encoder, here we include this cat encoder. Therefore, under each dummy variable or one-hot encoded variable, this cat encoder will be added. Similarly, for those transformed quantity features, this quan scalar will be added. And actually we have cat encoder, gender male, cat encoder, employment not working, and so on. And quan scalar age, quan scalar that's of CD4, and so on. So let's remove this cat encoder, these parts of these qualitative variables, and this part of these variables. So we have gender male in the newly transformed coverage data frame or input features data frame. Employment not working, employment part-time, employment unemployed, employment NAN. Therefore, here one thing that we have to notice that if there are some qualitative variables which are missing, so those missing values will be considered as a new category of that variable. And actually this is not good. We have to consider the use of imputation techniques in order to replace those missing observations. But for demonstrating the application of these machine learning techniques for survival analysis, I'm going to just consider these values as they are. So that means here employment has something like 1, 2, 3, 4, 5 categories, where the other category is considered as a reference category. So this value should be actually imputed using the different imputation techniques. Otherwise, those missing values are considered as new categories of those qualitative variables. Then we make a transformation on the covariates or input features data frame. Next, let's prepare that of the outcomes data frame. This outcomes data frame should be prepared into a form of what we call structured array. So in the train outcome, we have this defaulter, and the train time, let it be that of the survival time. And this train outcome should be converted into a Boolean variable. So here we have to add this dot as type bool variable, so that the values are like true or false. So here let's check first. Let me remove this one. Let me remove this and let's see the results. Now these are event of interest with values 0 and 1. But here we need to convert for modeling the machine learning models for survival analysis. The event variable should be a Boolean data type. So here we need to add this dot as type bool, so that the zeros will be converted into false and the ones will be converted into trues. So false, false, true, true, and so on. So this outcome event of interest should be a Boolean data type. So the survival time, it can be as it is. So here we have the train outcome, that is our event of interest. The train time is nothing but the survival time. Then let's tuplify these two outcomes. Why train tuple? Let the first be the train outcome, the second the train time. So here we didn't do any much change. What we did is actually put in the first place of this tuple the train outcome, in the second place of this tuple the survival outcome. Similarly, for the test outcome, we do the same. We have test outcome, defaulter, we have test time, the survival time. And let's simplify. Now, this variable constitutes the first as the outcome or the event of interest, which is actually converted into a Boolean type. And in the second place of this tuple, the test type are presented or placed. Then once we simplify this outcome data of the train and outcome data of the test, we can convert into that of a structured array. So for that purpose, we need to import this function from skserv util, we need to import this serv. Then this will convert that's of the survival outcome variables into a structured array format. So why train serve from arrays? The first one should be that's of the train, that's of the event of interest, and the second one is the survival time. So here the first value should be that's of the event of interest, which is actually Boolean. The second one should be that's of the survival time. And this whitetest table, this is also the same, just instead of this I can use this one, but here it is for the test, so I need to change test. We can do in this form, or it can be also in this form. This is nothing but this. The asterisk is here. Whitest tuple is a tuple which consists of the event of interest in the first place and the survival time in the second place. Therefore, here I have two values. These two values are unpacked here. So the first will be the test outcome, the second will be the test time. So both of these are the same, but I used just different ways of placing these values. Otherwise, both of these are exactly the same. So let's see what this structured array actually looks like. So this is now this structured array pairs each event with their corresponding time. So here, for example, in the amplify, here first we put our outcome of interest, false, false, true, true. Next, the survival time. We do the same here. First, that's of the outcomes as true or false. Next, the test time, something like here. So this structured array actually pairwises or creates a pair of each event with their corresponding time. So for example, here the first individual didn't experience the event and the time is 25.16 months. Second didn't experience, third didn't experience, the fourth one experienced the event of interest and at 45 months, and the last the same. And the same is true here for the test data frame. Again, this structured array format is false value, true value, and so on. So this structured array is nothing but it is a means of combining each event with their corresponding survival time, or time to event, or time to censoring. So we need to pre-process the train and test outcomes data into this form of structured array. That means we have to convert our outcomes data, which consists of the event of interest and the time to event, into this form, or what we call survival structured array format. Now we are ready to train some of the survival models. Now let's import the model classes from their corresponding package. So Cox PH Survival Analysis and Coxnet Survival Analysis are imported from skserv.linear model, random survival forests, extra survival trees, gradient boosting survival analysis, and component-wise gradient boosting survival analysis are imported from skserv.ensemble. and fast survival support vector machine and naive survival support vector machine are imported from skserv SVM, and lastly survival tree is imported from skserv tree. So let's run this cell. Now all these model classes are imported. So let's start from that of the Cox PH model. So the model class is Cox PH Survival Analysis. So first we have to instantiate our model class. And if I run this cell, it becomes something like this. Here alpha just will come back later. It is the regularization parameter. And the treatment of ties is by default the Breslow approximation. But if we are interested, we can change them into other methods for treating the ties, like that of Efron and other methods. And this is the number of iteration. If you are interested, you can change, but by default is 100. And we have just other additional parameters. So now the model is not fitted yet. This is just an instantiation of the model class Cox PH Survival Analysis. Once we instantiate our model class, next we can call the method dot fit over the instantiated class and supply the training data, where the first is that's of the training input features or coverage data, and this one, the second one, is the training output features or outcome data. So here X train is the one that is the transformed coverage data. This data, which is the transformed one, and regarding the outcome here, Y train is that's of the outcome features data which are in a structured format. That means here this format where just each pair of events and their corresponding time are combined together. So this is the information of the first individual regarding the event of interest and the survival time, and this one the second one, and this one the third individual, and lastly these values. This is just the structured array format of the outcomes data for our survival analysis. So we need to call this method and supply the training input features and output data, and then let me run it. Now if I point to it, it says fitted. Now this Cox PH survival analysis model, which is actually similar to the standard Cox proportional hazards model, is trained. So this, since it is a standard pH model, we can look at the coefficients of the model. So Cox PH dot, let me say coef, to see the coefficients. So here's the coefficient of the first input feature, this one the second, and so on. Totally here we have 12 coefficients. And if we are interested on the intercept, we can also but I'm not sure whether it displays the intercept, but let's check intercept. Okay. Yeah, so I think since it is a Cox PH model and that's of the intercept or that's of the baseline hazard is left unspecified or it's not estimated, so I think there is no intercept attribute associated with this Cox PH model. So there is no intercept term for the Cox proportional hazards model because the baseline hazard function is left unestimated or unspecified. So let me remove this one. So these are the coefficients or the parameter estimates corresponding to each of the input features. So for better visualization, let's associate each of these parameter estimates with the coverage names. So these are the 12 input features. So for male, here we have the coefficient 0.45. That means the males are more likely to be defaulted than females. For that of the employment not working is negative, and for the missing values of employment variable, it is actually negative. So here in this demonstration, I didn't use any imputation technique to replace the missing values, but in general, these missing values should be replaced by certain values, or the missing values should be imputed using a certain imputation technique. But for this illustration, I just considered the missing values as they are. And here, when consider clinical stage, it's 0.75. So when the patients are in clinical stage 4, they are more likely to be defaulted. It may be maybe due to just those patients in the severe clinical stage are more likely to be died. And when it comes to CD4, it's negative. Therefore, an individual with higher CD4 count is more likely not to be defaulted. And the same is true for that of age. Yeah, and those individuals whose functional status is working, they are also less likely to be defaulted. So these are the coefficients for the standard Cox PH model, or these are just the log hazard ratio values. Now, once we estimate this model, we can make predictions. The first prediction will be on that of the time-independent risk scores. And for that, we can use this dot predict. So the relative risk or the hazard is a measure that an individual will experience the event of interest at a certain given time compared to the others. So the risk score or the relative risk is actually, it's not a probability, but it is just a ranking or scaling of the risk. So higher risk scores implies the greater likelihood of experiencing the event of interest sooner, and this risk or hazard is actually defined as the linear combination of that of the covariates. So they just, let's say, the Cox PH model, where h naught of t is the baseline hazard function, and here we have e the power of beta 1 x1. This should be beta 1 x1. Is the power of beta 1 x1 plus beta d xd. So here the linear predictor beta 1 x1 plus beta 2 x2 plus beta d xd represents that of the risk score or the hazard. So this linear combination of the covariates is nothing but the risk score. So if this linear combination is 0, it's a baseline risk, and if it's negative, that indicates a lower risk of experiencing the event of interest. And when this linear predictor is greater than 0, that's an indication of higher risk of experiencing the event of interest. So here we have Cox PH model fitted here. Then over that, we can call the method predict and supply the test data to get the predicted risk scores. So here, if I run this code, These are the predicted risk scores of each individual. So this is a time independent, or let me examine the length lane of this score. Yeah, 440. There are 440 individuals in the test data. So these risk scores are time independent measures of the risk associated with each individual. Here for individual 1 is less likely to experience the event of interest. For individual 2 it's positive, so it may be more likely to experience the event of interest. For the third again it is negative, which indicates less likely to experience the event of interest. And this one is positive, which is more likely to experience the event of interest. So let me comment this just for now, and we can visualize this risk scores graphically to have a certain intuitive understanding. So let me run this cell. So this is just the distribution of the risk scores of the individuals based on that of the test data. So here the distribution is almost normal, therefore we can say that there is a balanced risk population. That means number of individuals in higher risk and low risk are almost equal. But in case if we would obtain, let's say, a longer right tail, in that case that is an indication of some individuals having a higher risk of experiencing the event of interest. On the other hand, if we have a long left tail, that indicates the presence of a few individuals who have a lower risk of experiencing the event of interest. So for this particular case, the distribution is centered around 0, therefore there is a balanced risk. This is a balanced risk population. And if we are interested, we can also group the patients by risk level. And if we use, let's say, the dividing the risk scores into 3 parts, into 3 quantiles, let the first one be the lower, next the higher, and then high. We can also look at this in this form. So each individual is categorized as like low risk category, medium risk category, and high risk category. So these are the risk scores, which are time independent predictions based on the Cox PH model. And the next prediction will be on the cumulative hazard, which is actually a time-dependent risk score, and for that we can use this predict cumulative hazard function. So the cumulative hazard function is nothing but it is just the cumulative sum of the hazard over time, or it represents the total accumulated risk of the event of interest up to time t. And mathematically we express in this form, where the cumulative hazard of each individual I is the area of the hazard function starting from 0 up to time t. So hazard is defined as a risk per instant of time, and the cumulative hazard actually measures how much risk is accumulated up to time point t. So this cumulative hazard actually starts at 0 and monotonically increases as the time goes on. And finally, the cumulative hazard is going to be 1. So this is a time-dependent measure. That means here we are going to predict the cumulative hazard of each individual at each time point. So for that, let's call this method predict cumulative hazard function and supply the test data. as it is. So let's see. This will produce that of the cumulative hazard values of each individual at each particular time. So it's taking some time. Okay, yeah. So here, just the first one is going to be the cumulative risk for individual 1, and yeah, the second one, and so on. So this is just the cumulative hazards of each individual at each time point. For better visualization, let's just use this function. For example, for the first 10 patients, these are the predictions of the cumulative hazard of each individual. So here we can see that this individual, I think it's patient 7. It has a higher risk of experiencing the event of interest compared to the other individuals. And based on the classified here risk scores, low, high, medium, we can also visualize the cumulative hazards by risk group, and let's see which group has actually a higher risk of experiencing the event of interest. So it's something like this. So here you can see that the high risk group patients will experience the event of interest sooner, and next the medium risk group patients, which is here the orange one, will experience the event of interest next, and those individuals in the low risk scores have a lower cumulative hazard throughout the different time points. And the third prediction that we can obtain from this machine learning models is the survival function, which actually measures the probability that a patient is still surviving, or in particular, based on our data, not defaulted at time t. So the survival at time t is nothing but the probability that the individual will survive beyond the time t. This is actually e to the power of -1 times that of the cumulative hazard. So if the survival function drops quickly, that indicates the model predicts high risk, or in other words, it indicates shorter survival, or the individual is more likely to experience the event of interest sooner. On the other hand, if the survival stays near 1, that indicates that a low risk or longer survival times, so that the patient is less likely to experience the event of interest. So here we can obtain the patient-specific survival function or probability using the method .predict survival function. So like that of the cumulative hazard function, this displays also the survival probabilities of each individual at each particular time point. So here this survival function is obtained using this function .predict survival function, and supplies us of the test data, which will display the survival probabilities of each individual at each time point. So this one is for the first individual, and same continues for the second, and so on. And here we can view as, let's say, the length of these survival probabilities, it is 440, but each individual has a predicted probability at each time point. So the first component is actually here. This is the first component that indicates actually the time points and the survival probabilities. So let me comment this one and let's see. The first component is that of the time points. These are the time points of each individual. And the predicted survival probabilities at each time point is this one. So at time 6, the predicted probability is this one. At time second one, the predicted probability is this one, and so on. So like that of the cumulative hazard function, this predicts the probability of survival for each patient at each particular time point. We can also visualize the survival time graphically, this one. So here the cumulative hazard was something like this, but the survival function or probability is actually a function of the cumulative hazard function. So the survival function or probability looks like this one. So the survival time of this individual, maybe that's of individual 7, is shorter compared to all the other individuals for this sample of the first 10 patients. We can also visualize the survival times by the risk group that we have classified before, using that of low, medium, and high. So we can execute this cell, so it's something like this. So those in the high risk group are having a shorter survival time, and the medium have some higher survival time, and those in the low risk group have higher survival time. Then we have seen here how to fit the Cox proportional hazards model using the model class which is actually called Cox PH survival analysis. So once we fit our model, next we need to assess the performance of the model. So for this purpose, we are going to use the performance measures. So some performance measures depend on that of the time-independent risk scores, and others depend on the cumulative hazard function, and the others depend on the predicted survival probabilities or survival function. So the measures that depend on the time independent risk scores are the concordance index measures and the cumulative dynamic AUC. And the measure that depends on the time-dependent cumulative hazard function, we have a cumulative dynamic AUC, and Breyer score and integrated Breyer score depend on the time-dependent survival probabilities. And here this concordance index and cumulative dynamic AUC can measure the ability of the model's discrimination, and similarly this cumulative dynamic AUC is also for assessing the model's discrimination ability, and this Breyer score and integrated Breyer score are not only used to assess the model's discrimination, but also they are used for assessing the calibration ability of the model. So this diagram is actually taken from the scikit survival documentation. Then if you click here, the Documentation will show you the performance measures that can be used for evaluating the survival models. So you can look at here the details of these performance measures, and you can also find course like here how to get or determine these different performance measures for assessing the performance of the model in its in terms of discrimination and thus of calibration. So the first measure that we are going to consider is that of the C index, which is the default performance measure in circuit survival. So this measures the model's ability to correctly rank the survival times, and it is actually the generalization of the area under the receiver operating characteristics curve. So a larger value of the C index is an indication that the model is better. And actually, this C index is not actually a measure of the actual survival probability accuracy. Rather, it measures simply the relative risk ranking. Otherwise, it is not an indication that the accuracy of the actual survival probability. So this is the default metric. So over the fitted model, we can call the method score and pass the training data to get the training C index value, and call the method score and pass the test data to get the test score. So let me run it. So the C index is around 66.3% for the training and 61.4% for the testing. So this is the default metric in circuit survival. Now let's import all of these performance measures from skserv matrix, concordance index censored, concordance index inverse probability censoring weights, and cumulative dynamic AUC value, the Breyer score, and the integrated Breyer score. So these performance measure classes are imported. So let's start from that of the concordance index censored. Actually, this is the same with that of this C index measure, which is the default metric in circuit survival. So this concordance index sensor depends on the risk scores, the predicted risk scores, the time-dependent risk scores. So we need to get this one, the predicted risk scores. Let's say first based on the training data. Then we can call this method concordance index censored and supply the training output data and thus of the risk scores here. So this provides a tuple of 5 different values. The first is actually the C index. The second is will display the number of concordant pairs, and this one will display the number of discordant pairs, and thirdly it will display the tide risk, and lastly the tide time points. So let me run it. So the train C index is 66.3%, which is actually the same with that of this value. And this is the number of concordant pairs, number of discordant pairs, and the number of tide risks, and lastly the number of tide time points. And for the test, we need to change, instead of xtrain, we need to use xtest, and the same function is used. Now 0.61 or 61.44% is the C index for the test data, or this is actually is 1. So this concordance index censored returns as of the C index measure, which is actually the default metric in scikit survival. So here the concordance index or C index measures how well the model's predicted risk scores rank the survival times. Just it is a comparison of the predicted risk scores and thus of the survival times. So the higher is the better. And the concordant pairs indicates the number of comparable pair of observations where the model correctly observed the risks. So the higher the risk is an indication that there is a shorter survival. And the discordant pairs is the number of pairs where the model risks the ordering is the ordering was wrong, right? So yeah, it is just the opposite of these concordant pairs. And the tied risk pairs indicates pairs where the predicted risk scores are equal or no ranking is possible. And there could be also pairs that are not comparable, where the number of pairs that could not be compared due to censoring rules. So for example, if patient A died, let's say at 5 months, and patient B is censored at 6 months, here the comparison is valid because the death time of A is known. On the other hand, if patient A is censored at time 5 and patient B is censored at time 6, here the comparison could be invalid because we don't know who would have died first. So here this concordance index censored returns this index value, number of concordant and discordant pairs, the tied risks, and the tied time points. And there is also another measure of this index, which is called concordance index IPCW or concordance index inverse probability censoring weights. This is actually designed to handle sensor data in a more robust way using the idea of inverse probability censoring weights. So this performance measure actually provides a less biased estimate, especially in the case of having a high level of censoring. So for this concordance index inverse probability censoring weights, we need to supply the training data and test data for calculating this inverse probability censoring weights. So as usual, this depends on the predicted risk scores. So we need to obtain these values, the predicted risk scores based on the test data. And then here we need to provide that of the train and the of test outcomes data. So this returns like that of the C index measure, the C index, the number of concordant and discordant pairs, the tied risk and tied survival times. So the concordance index based on the inverse probability censoring weights becomes 0.57, and this is actually assumed to be less biased compared to the standard C index measure, especially when you have a larger number of censoring, a larger number of censoring. And the other is the cumulative dynamic AUC. This is also a time-dependent version of the area under the curve designed to handle that's of the event and censoring discrimination at multiple or at different time points. So it is a measure of how well the predicted risk scores can discriminate between individuals who experience the event before a certain given time and who do not experience the event of interest before that given time. So for this purpose, first we need to obtain this the test times where the predictions are going to be made. So here what I did is just based on the test outcomes data, the minimum value, and here the maximum value. And let's select just 10 points between the minimum survival time and the maximum survival time of the test data. Then you can also get the usual risk scores based on the test data. Then the cumulative dynamic area under the curve can be determined by supplying the training and testing outcomes data and the predicted risk scores here. And also it needs the test time points where the predictions are going to be made. So let me run this. So the first value is going to describe that of the AUC values at each time point. Now it is done. Let's see the values. So this is just the AUC in the first time point, in the second time point, in the 10th time point, because here we just selected these 10 time points between the minimum and the maximum test time points. And the average is going to be 0.6147. And let's visualize this. So this is actually the time dependent that's of this cumulative dynamic AUC. And this is actually the average of the cumulative dynamic AUC. So here, for example, before, let's say this time point, let's say for time point 24 and less, the performance is somewhat good, especially at time point 0, the performance is exceptionally high. But when the time goes from time point 30 and onwards, the performance of the model is somewhat lower. So the performance decreases for time points above this one. So we can say, especially the model, the Cox PH model is especially good in predicting the default times at the initial time point. There is also another measure which is called Breyer score, which measures both the calibration and prediction error over time. It's not only discrimination like that of the C-index AUC. So here's this cumulative dynamic AUC, and that of this C-index measures actually measures the performance of the model in terms of discrimination, or in terms of identifying individuals who experience the event of interest and who do not experience the event of interest before a certain given time. But this Breyer score measures both the calibration and prediction ability of the model. And this Breyer score in Breyer score we need the values to be smaller. Therefore, a smaller Breyer score value indicates that the model is better. So previously we obtained this the predicted survival probabilities. So the predicted survival probabilities you have, yeah, this one, just predicted survival probabilities. Here we have, this is actually a step function of each individual because it represents the predicted survival probability for each individual at each time point. Therefore, these probabilities are actually step functions. So here, to determine that of the Breyer score, first we need to create that of an array form of the survival probabilities. So for that we use just this function to convert the step function of the survival curves into a certain predicted array format. This is actually the predicted survival probabilities, which is a step function for each individual. So using this function, we can convert into an array form of the survival probabilities. So these are just array form of the survival probabilities for individual 1, for individual 2, for individual 3, and for the last individual. Then once we obtain the array form of the survival probabilities, here we can get the Breer score by supplying the training and testing outcomes data and the array form of the survival probabilities, and we need also the test time points. So here let me run this. So these are the Breer scores. Breer score at time point 1, the lower is the better. Breer score at time point 2, and so on. Breer score at time point 10, because here the test time points has 10 different values. So yeah, so here these are the Breer scores. So this is a time dependent. We can also get just an integrated Breer score, which summarizes these values into a single value. So the integrated Breer score is 0.14. So a model with a lower integrated Breer score is better. We can also plot these Breer scores and the integrated Breer score, and so that we will be able to visualize and have a certain intuitive understanding. Name times is not defined. Okay, so yeah, so I need to change this with test times. Test times, yeah. So the Breer score for the lower time points or for the initial time points are lower, but the Breer score becomes higher for higher time points. And here the broken red line represents the of the integrated Breer score, or the overall summary of the model in terms of the Breer score. So this plot actually shows how the prediction error changes over time by using this integrated Breer score as a summary. So the prediction error increases when the time increases. On the other hand, the prediction error is lower for the lower time points. So now we have considered the standard Cox PH model. Now let's consider that of the penalized version of Cox models. So the first one that we are going to consider here is that of the Ridge Cox model. So first let's obtain the standard Cox model here and supply the training data to train the model, and let's obtain the C index based on the training set and the C index based on the test set. Now this is just the standard Cox model that we have seen before. So this is the standard Cox model with 66.35% of C index and 61.45% of C index for the test set. So to fit a rich Cox model, here in the instantiation we can set the value of alpha as a value greater than 0. So let it be 1. By default it is actually 0, but let's set it to 1 and let's fit our model and get the training and testing C index values. Then this becomes something like this. So in fact there is no much difference. Yeah, the difference is actually very small. Let me increase this to 10. when the parameter or the ridge effect is 10, the test performance becomes 66. It shows a slight decrement over the standard Cox PH model, and the test performance, it shows a slight increment, right? Similarly, if we increase this to 100, the test performance, the train performance again shows a decrement. The test performance shows a slight increment. So here we can actually let's say here get the different parameter values when we use different ridge effects. So here let's select 50 values for the ridge effects. This alpha between 10 to the power of minus 3 and 10 to the power of 5, and let's select just 50 values. That means here I can see the values as this one. So let the first value for alpha be 1.000 times 10 to the power of minus 3, and the next 1.5 times 10 to the power of minus 3, and so on. Total here we have 50 values. So for each value we can fit a model, and we can select the optimal value of alpha that works best. So here we can visualize in a data frame format. So for example, when the first value of alpha is this one, that is 0.001, the coefficient for gender male becomes this one. When it is 0.0015, second value, it becomes something like this. The third is one, and so on. So this shows actually the changes in the parameter estimates of the different overrides for different values of the ridge parameters or shrinkage effects. Maximum value here we take for the ridge effect is 100,000, or that is 10 to the power of 5, and the smallest value is actually 0.001, that is 10 to the power of minus 3. But instead of looking these values in terms in this form, in a table format, it is better to visualize. So the plots become something like this. So for example, when the ridge effect is 10 to the power of minus 3, one of the parameter estimates associated with the covariates is around let's say minus 0.5, and this one around minus 0.4, and here we have three parameter values around minus 0.2, and 2 here around 0, and the other parameter values, let's say above 0.2. But when we increase, let's say, the shrinkage effect alpha to 10 to the power of 0, that is, if we make the shrinkage effect alpha to 1, now most of these parameter estimates gets a smaller value, or they close to the value 0. But if we make it 10 to the power of 2 or 100, now the parameters are again getting closer to 0. But if we make the parameters, that's of the shrinkage effect parameter, to 10 to the power of 5 or 100,000, all of the parameter estimates become 0. So increasing that's of the ridge effect, or increasing the ridge parameter, forces the parameter estimates to go closer to 0. So we need to determine the optimal value of the shrinkage effect or the ridge parameter. So for that we can use what we call results of grid search cross validation, which is a method of tuning hyperparameters. So our particular hyperparameter is that of the ridge parameter or the shrinkage effect. So if you click here, the grid search CV will be displayed. So here we need to provide the estimator or the model of interest, and here we need to list all the parameter values of the hyperparameters, and there are also other options here. So you can look this documentation for further understanding how this grid search CV can be used for tuning the hyperparameters. So we need to import this grid search CV class from scalar model selection. And first we need to instantiate our model of interest, Cox PH Survival Analysis. So let me run it. Now this class is imported and we instantiated this model. Next we need to define the values of the hyperparameters. Our hyperparameter is alpha. So for this hyperparameter, here we have to define in a dictionary format. That means in this curly braces, alpha, then let it be NP log space from -3 up to 50 values. That means it is just selecting evenly distributed alpha values or ridge parameter values from 10 to the power of -3 to 10 to the power of 5. So we need to define this. So these 50 values defined here are nothing but the one that starts from 0.003 to here we have 100,000. So what the grid search CV does is it fits one model based on each of these shrinkage effects and selects the model that works best. Then we need to call this grid search CV and supply the estimator. The estimator is nothing but our model of interest. Our model of interest is this ridge Cox, this one. Then this ridge Cox has option alpha. Then the hyperparameters param grid equals hyperparams. These hyperparams are nothing but these values. This alpha is nothing but exactly the same name with this one, alpha. We need to vary or consider different values for alpha. And let the number of cross validations be 10. And finally, by default, it returns the test performances. If we are interested to get also the train performances, we can set this return train score to true. Then this will perform a grid search models by fitting one model for each of these hyperparameter values. Again, this grid search is an instantiation. Here you can click the parameters are the estimator is Cox PH Survival Analysis. This one, ridge Cox. This ridge Cox is nothing but this one. And param grid, here you have alpha. Array starting from this up to this is not totally visible, but this alpha is nothing but these values. Number of cross validations, we set it to 10. And we also requested to return the train score. And here for the Cox survival analysis, we have the parameter by default alpha is 0 because it is the standard Cox PH model. But based on these hyperparameter values defined here, the alpha values are going to be vary. So this grid search model is just an instantiation. So to train all the possible models based on this list of hyperparameter values, we need to call the method fit and supply the training data. So this will fit one model based on each of these hyperparameter values. So let me run it. It may take a little bit some time because it is going to fit 50 different models based on these hyperparameter values, which are actually 50 hyperparameter values or 50 alpha values. So it may take a little bit some time, and we can examine the results once the training is done for these grid models. Alright, now the research models is the training of the research models is done. So here we can look at these are the specifications of the research model. Now here says best estimator. So here the value of alpha of these different 50 values, the value of alpha with a better performance is 1.8421. So of the 50 different models, the model with alpha equals 1.84 performs better. So this is optimal value of alpha. Initial by default here it was 0, but now the optimal value is 1.8421. So here actually this if we call CV results this attribute over the grid models, this will provide a dictionary, but this dictionary is not that much treated for ease of observation. So it's better to convert into a data frame. And again, this data frame also consists of so many rows and columns. So let's just extract these values only: the alpha value, the mean test score, mean train score, and the rank test score. Now totally here in this hyperparameter values we have 50 values. So there is one model for each hyperparameter value. So here starting from 0 we have 49. That means we have 50 models. The first model is based on alpha this with a mean test score 64.5%, a mean train score 66.4%, and so on. Second one, third one, and lastly the 50th one. So of these 50 candidates reach parameter values, the one that has a better performance is this one with a rank of 1.8421. So this value can be considered as the optimal value of the reach parameter for the Cox PH model, or for the reach Cox model. So once you obtain the optimal hyperparameter value, in fact we can also get the optimal hyperparameter value by calling this best params and name of the hyperparameter. So this value is actually 1.8421, and the best score is actually 64.65%. So based on this optimal hyperparameter value, we need to fit our final model, alpha 1.8421. Then this reach Cox, we can obtain the score, reach Cox.score, the training data to get the training performance, and reach Cox.score, and then supply the test data to get the test scores. So this can be considered as something like our final reach Cox model. And the other is lasso and elastic nets Cox models, and for that we are going to consider the Cox net survival analysis. Let me comment this Cox net survival analysis is a survival model that combines both the L1 and L2 regularization techniques, or that combines the reach and lasso Cox models. So let me run this. So here is this CoxNet model. Here this model is going to have some parameters. The first one is here L1 ratio. This is the ratio of the L1 and L2 regularizations. So L1 ratio by default it is 0.5. That means L1 is going to have a 50% contribution, and L2 will have also a 50% contribution. And the other here, we need to also specify that's of the alpha parameter. So here alpha is a description. Just using this help function, you can look at the different values for specification. L1 ratio is default 0.5. So let me instantiate this CoxNet survival analysis. CoxNet survival analysis, let's say init Cox. As we saw before, now this is just an instantiation. The model is not fitted yet. So L1 ratio by default is 0.5. Alphas, we can determine the ridge effects. So specifically for this CoxNet survival analysis, we are going to have mainly two hyperparameters, the shrinkage effect alpha and the L1 ratio, which makes a balance in between the L1 and L2 regularization techniques. So once we instantiate this model, we need to call the method fit and supply the training data. So now the model is fitted, and the parameters by default L1 ratio is 0.5, and that's of alpha, it's by default set as actually none. And let's obtain the scores. Now this init or elasticnet Cox model has 66.35% for the training data and 61.55% for the test data. Actually, it doesn't have a significant difference with that of the standard Cox PH model. Now, by default, L1 ratio is 0.5, and let's make it L1 ratio as 1. Now, when you make this L1 ratio as 1, that means the contribution of the L1 regularization is fully taken, but the contribution of the L2 regularization is ignored. So this model is the same with that of Lasso Cox model, because L1 ratio is 1. Lasso Cox model. So this Lasso Cox model, let's alpha be 0.05, and let's fit the model and see the outcome. Now the model is fitted. Let's see the coefficients of this model. Just Lasso Cox, calling the method of underscore. This is just for removing a certain the additional extra dimension. Now here you see all the parameter estimates are 0, but here just we have only one parameter which is different from 0. So as we know, just the lasso regression or L1 regularization sets some of the parameter estimates to 0. So here that means this 0.05 is very large because it makes almost all the parameter estimates to 0. So let's decrease it to 0.05. Let me run this again, and let's see the coefficients. Now some of the coefficients are 0, but the others are different from 0. Similarly, if I add again, if I make this alpha small, now here almost here we have one parameter estimate. that is set to 0. So when this alpha is larger in the lasso Cox model, that means we are forcing some of the parameter estimates to close to 0. Therefore, as long as the value of alpha is higher, we are forcing most of the parameter estimates to be close to 0. So as we know, just these lasso regression models are models something like that can be used for feature selection because it sets some of the coefficients to 0. So with this value, just let's see the scores of the training and the testing, and let's visualize and compare the performance to the previous one. Now here this is the ridge effect or the ridge Cox model. So when the shrinkage effect increases, all of the parameters will be forced to be close to 0. But when it comes to the lasso Cox regression model, some of the parameters are immediately goes to 0 sooner, and finally all of the parameters are goes to 0. So here, for example, when the shrinkage effect is around 10 to the power of minus 3, some parameter estimates get close to 0. For example, this one and this one. And when the shrinkage effect is 10 to the power of minus 2, some of the parameters are set to 0 here. And in general, if we make the shrinkage effect for the lasso Cox model as 10 to the power of minus 1, almost all the parameter estimates are set to 0. So this lasso regression uses that's of what we call L1 regularization, and the ridge Cox model actually uses that's of the L2 regularization. And when you say this elastic net regression, now it uses both the L1 and L2 regularization techniques. So here, for example, let's the L1 ratio be 0. Let me remove this. Then if we set the L1 ratio to be 0, that means the model ignores the L1 effect. So it is only, it's considering only the L2 regularization. So this seems just a ridge Cox model. So let's try and see the outcome. So here, even if here when this L1 ratio is 0, even if we assume this model is similar to the ridge Cox model, the L1 ratio parameter should be between 0 without increasing 0 and 1. So if the L1 ratio is 0, this model will not run, or this model will not be trained. But instead, if I make something like 001, very small number, this is almost a ridge Cox model. So in that case, it may work. But if we make it fully 0, it doesn't work, which is actually theoretically, which could be the same with that of the ridge Cox model. So when we make this L1 to a very small number, something like this, that means this is almost a ridge Cox model, ridge Cox model. But if we make this as 1, something like this model is going to be what you call, instead of ridge, it is what? A lasso Cox model. Lasso Cox model. But for now, let me consider something like this. Now, for the Cox net survival analysis, mainly we have two hyperparameters. One, the L1 ratio, which makes a balance between L1 and L2 regularization. So if this L1 ratio is very close to 0, that means we are considering more a ridge Cox model. But if this L1 ratio is 1, in that case, we are considering that of the lasso Cox model. But if the value of the L1 ratio is between 0 and 1, we are having the effect of both lasso and ridge effects, or L1 and L2 effects. So here, using that of the grid search algorithm, we can optimize, or we can find the optimal values of the L1 ratio and the shrinkage effect alpha. So here, this Coxinet model, we have alpha, the shrinkage effect, and we have this L1 ratio, this one. Therefore, we have mainly these two hyperparameters. So let the L1 ratio be NP linear space between 0.1 and 0.9, and let's select 20 values. This is nothing but selecting 20 evenly distributed values between 0.1 and 0.9. If I run this, so for the L1 ratio, we have these values from 0.1 up to 0.9, 20 different values. And for the alpha, let's consider these three values. Therefore, here we have 20 values for the L1 ratio, and you have three values for the alpha. 20 times 3, it's 60. Therefore, here we are going to fit 60 different possible models for each combination of these two hyperparameters. And we need to select the one that works best. So this is just the thing, or the idea, that this grid search CV is going to be applied. So grid search CV, the model is this ElasticNet survival model. The parameter grid, here we have defined these hyperparameters here. Let the number of cross validations be 10, and let the return train score be true. This one doesn't have an impact, but in case when it provides an error, it will directly indicate what type of error occurred, or the source of the error. So this is just the instantiation of the grid search model. Then after that, to fit the different models based on this specification of hyperparameters, next we need to call the method fit and supply the training data. So let me run this cell. And again, since it's going to fit 60 different models based on these combinations, so it's necessary, it may take a certain time. So it provides an error. Let's see the error. Bool objects has no attribute all. Okay. So actually the training is done, but this error is not actually related to the model that we are training here. It is related to the display structure of the notebook. So actually here the grid search CV is trained here. So maybe let me use print something like this. Yeah, so the problem is not related to the code, just it is the way that the results are displayed in the notebook. So here cross validation we have 10 and the parameter values, and for the L1 ratio also here we have these different values. So from this, the first one displays that of the measures of, here let me make it here we can see that we have L1 ratio, and I think we need to add here alphas. Let me add here another alphas. Let me try. Yeah. So here, the one that's ranked one is an L1 ratio of 0.142105 and alpha of 0.001. So the best values, best L1 ratio is 0.1421, best alpha 0.001, and the best C index score is 64.67%. So lastly, we can fit our model based on these specifications. So the L1 ratio here is not 0.6052, but it is 0.1421 and alpha 0.001. Let's fit all the training data and get the performance on the training and testing sets. So for this ElasticNet model, the performance on the training is 66.3%, and on the test it is 61.62%. So in general, the Cox proportional hazards model can only predict risk scores that are independent of time due to the built-in proportional hazards assumption. In contrast, when it comes to that of the most of the machine learning models, like that of the random survival forest, survival support vector machine, and so on, they do not have this proportional hazards restriction. So now let's start that of fitting a random survival forest. Like that of the definition of a Cox proportional hazards model, what we are going to do is first we need to instantiate our model class. Random survival forests, let the random state be 42. This is the instantiation. Then after that, we need to call the method fit and supply the training data. Then after fitting, we can call the method score to get the C index, and then the training data for getting the C index based on the training data set, and the test data to get the C index for the test data set. So let me run this. So here the training performance based on this random survival forest is 0.89 and the testing is 0.58. Similarly, we can also get based on this random survival forest, we can predict the risk scores. So for that, under this fitted random survival forest model, we need to call the method predict and supply the test data. Then we can also obtain the cumulative dynamic AUC by supplying the training and testing outcomes data and the risk scores predicted and also the test times. So let's visualize this one. So this is the cumulative dynamic AUC based on that of this random survival forest. And similarly here, you can look at the parameter specifications of this random survival forest by using this help function. So this help function provides random survival forest. It has some parameters, number of estimators, 100. This can be fine-tuned and minimum samples split, and minimum samples leave, and so on. So this can be considered as hyperparameters to be optimized using that of the research CV. So now let's consider these three hyperparameter values. One, let the number of estimators be 5, 10, 20. By default, the number of estimators is 100. So let it be 5, 10, 20, and the minimum samples splits let's be 4 and 6, and the minimum samples leave let's be 4. So first we have to instantiate our model of interest or estimator. So here we have three models. Here we have 2, 3 times 2, 6. Here we have 1, 6 times 1, 6. Therefore, based on these three hyperparameters, 6 different models are going to be fitted using this research CV. Then the one that provides the higher performance will be considered as a better model, and the corresponding hyperparameter values can be considered as optimal values. So we need to call this research CV, and our estimator is this random survival forest. The parameter grid, here we have these hyperparameters defined. Let the number of cross validations be 10, and let's return the train score. And lastly, over these grid models, we need to call the method fit and supply the training data as X train and Y train. So this will provide, as usual, the cross validation results, and we can obtain the optimal hyperparameter values. So of these three hyperparameter specifications, the minimum sample slip 4, minimum sample split 4, and number of estimators 20 is represents as of the optimal values of the hyper parameters. We can also get directly those values. So the optimal number of the minimum sample slip is 4, minimum sample split is 4, number of estimators is 20, and it is best cross validation score is 61.66%. So based on these optimal values, we can fit our final model as number of estimators 20, mean samples split 4, and mean samples leave 4. So the training performance is going to be around 84% and 57%. But these two scores have a great difference, so still this random survival forest model seems to have an overfitting problem. Therefore, a further refinement or tuning the hyperparameters of these random survival forests should be considered, or further tuning is required, because the difference between the training and the testing performance are quite different. This is an indication that the model random survival forest is overfitting. And the other, we can also consider the gradient boosting survival model. So like the previous ones, we can instantiate the model gradient boosting survival analysis, and then we can fit our model by supplying the training data, and we can get the training and testing performance scores. So here the performance here, it becomes 73 for the training set. For the testing, it becomes around 61. Then compared to this random survival forest, where the training performance is 89, the test is around 58. This gradient boosting survival model has a training performance of 73 and a testing of 62. So this model seems to better compared to the this one, the random survival forest, because this model is more likely overfitting. And we can also get the cumulative dynamic AUC in the usual way. So the plot will be something like this. And similarly, for the component-wise gradient boosting survival analysis, we can instantiate this form as usual and call the method fit and supply the training data to train the model and get that of the training and testing performances. Now it becomes 63 for the training, and the testing performance becomes around 60.7%. We can also visualize the cumulative dynamic AUC. It is something like this. And coming to that of the survival support vector machine, we can instantiate our model of interest in this way. First, let me remove this one and let's see the default. And we can fit our model and get the performance scores. So it becomes 66.67% for the training and 62% for the testing. If we are interested, we can increase the number of iterations to 1000, for example. And again, the training and testing performance are something like this. And as usual, we can also get the cumulative dynamic AUCs, which will be in this form. And for the naive survival support vector machine, again, we have to instantiate the model and fit our training data and get the training and testing performance. So if I run this, and I can get the cumulative dynamic AUC for this model also, which looks like this one. And the same procedure is applied for the survival tree, which is equivalent with that of the decision tree to be used in regression and classification problems. So the survival tree should be instantiated and then fit the model and get the performance, which becomes 90 for the training and 90% for the training and 52 for the testing. And again, this model is overfitting because the difference between the training and the testing performance are quite large. We can visualize also the cumulative dynamic AUC, which is something like this. And lastly, we can also fit the extra tree survival model. Extra survival trees is instantiated here, and then we fit the model and get the training and testing performance. So the training performance becomes around 77% and the testing around 59.66%. And for the cumulative dynamic AUC, it is something like this. And let's visualize all the cumulative dynamic AUCs for all these models. So we have the Cox proportional hazards model, random survival forest model, the extra trees survival model, the gradient boosting survival model, the component-wise, I think, gradient boosting survival model, Here this is CGBS. Okay, so support vector machine, naive support vector machine, and the survival tree. Therefore, here when we compare the models, we can easily see that there is no single model that has a better performance in all of the time points. So, for example, initially up to time point 6, the models here is extra trees, the survival support vector machine, the gradient boosting survival model, and the naive survival support vector machine are almost equal. And when you consider the time point from 12 to 24, I think the gradient boosting survival model works better. And when you consider the time points 30, the naive survival support vector machine is better. And when you consider the time points from time point 36 to 48, here the extra trees model is showing a better performance. In the last time point, the gradient boosting survival model seems to show a better performance. So in such case, for example, if the objective is prediction, instead of using one of the model for making a prediction throughout this survival time points, it's better to consider each models based on their performance at each time point. And lastly, let's see feature importance to indicate which variable is most predictive of the outcome of interest or the survival outcome of interest. In the case of linear models, we can directly consider the magnitude or absolute value of the parameter estimates, which reflect the strength of the effects actually. So if we go back to the first Cox PH model that we have fitted, the ridge or the of the standard Cox model, you can easily see that here this is one. Here let's say uh, yeah, for the Cox proportional lattice model or for the ridge Cox model, elastic nets and lasso, we can consider the absolute value of these coefficients. So for example here, the one having a larger impact is clinical stage 4, and next is going to be the employment part-time, no, is this functional status bedridden and employment part-time, and so on. Therefore, based on the absolute values of these parameter estimates, we can be able to identify the relative contribution of the different factors that are included in the model. So for linear models, we just need to see the parameter estimates associated with the different covariates. And for the tree-based models, there is an attribute called feature importances. So by calling these feature importance attributes, we can identify the relative contribution of each variable. So for example, the gradient boosting survival model is a tree-based model. So over that, we can call this feature importance attribute. So the feature importance of the first covariates, second, third, and so on. Let's associate with variable names. So here, so here we can see that CD4 is having the largest contribution. Next, H is having the second contribution, and so on. But of these 12 different input features, CD4 and H have the largest contributions. So these feature importance are actually non-negative, and they measure the contribution in reducing the model's predictive error. So when CD4 is included in the model, the reduction in the model's error is 0.39, and when H is included, it is 0.28, and so on. But when you include this employment not working, the reduction in the model's prediction error is 0.004, which is very small. So the most important covariates in explaining the time to default of HIV patients are CD4 and H based on the data that we have used here. And there is also another method of identifying the relative contribution or importance of covariates, which is called permutation importance. And actually this permutation importance is model agnostics. That means it can be used for any model. It doesn't depend on the type of the model. So we can use permutation importance for linear models, for tree-based models, and for other types of models. So if a certain feature is negative, if a certain feature has a negative importance, that means that feature is contributing a noise to the model. So in that case, that feature is not useful. On the other hand, if the feature is useful, the feature importance is going to be positive. Then in that case, that means the feature is important. And if the certain feature has an importance of 0, that means the feature has no importance in general. It doesn't have an increasing importance, or it doesn't have a negative impact in the model's prediction ability. So this permutation importance can be imported from sklearn inspection, and then we can call this method permutation importance, and our model of interest, which can be any model, linear model, tree-based model, or any other model, and supplies us of the test data. And here we can determine the number of repeats. Let's say 15. Here the higher is the better, but when we increase this to a larger number, the computational cost will be by much larger. So this will display the relative contribution or permutation importance of the variables. So the idea is here, when the variable is removed from the model, by how much the model's error will increase or decrease. So these importance summaries are actually dictionaries. Importance mean, importance standard deviation, importance. So let's convert this into a data frame format so that we are in a position to identify features that are important. So these are the permutation importance. So here, when CD4 is removed from the model, the contribution is 0.004 in reducing the model's error, right? H 0.003. But when you come to those missing values, so these missing values are considered as a new category of the implement variable. So the inclusion of these missing values is bringing a negative contribution. So every time, as long as we have missing values, just imputing those missing values using certain imputation techniques is necessary. So for this particular case, because the null values are considered as one category of the implement variable, so this category is contributing noise to the model's prediction ability. On the other hand, when it comes to that of let's say something like clinical stage 3, and that's of clinical stage 2, their contribution is almost 0. But all the other variables have a positive contribution in the models, in bringing a reduction in the model's prediction error. So this permutation importance is a model agnostic method for identifying the relative contribution of the different covariates included in a particular model. So this is all about today's video. Thank you for watching.